so we're going to go ahead and get started. Any questions, comments, thoughts, things that we need to talk about before we dive into material today?
Is there an assessment that we're going to have to do?
There's an assessment for last week, but there's not one for this week.
Okay. I didn't see any week 3 assessments.
It might have been, so it was set up and there should be a due date, so it should be in your calendar.
Okay.
Desiree, did you get registered for the course?
Not officially. I'm still waiting. I need an email registration today, and then I'm going to talk with Professor Setchell in the lab today.
Okay, great. Yeah, I think that might be some of it. Did anybody else have a hard time finding it from last week? Greg, it looked like you were saying something, but then you went right back on mute. No? Okay, so it should be up. Double check. I think some of it was my fault, Desiree, that I hadn't posted it in the module, even though it was set as an assignment. And so I've set it up now in the module. I noticed that last night. So it's in the module. So go back and double check. And if you can't find it, let me know. And it might be in part because you weren't registered, so it doesn't show up on your calendar. So just let me know if you're having a hard time. But don't worry about it being late. I won't count it, late. This week, we don't have an assessment. I'm put it together with next week's assessment. So I kind of just put everything together for those two. Any other questions, comments, thoughts before we dive in? Okay, so there's a fair amount of material to cover today, and I actually decided to cut the first part. So the first part of it, we're going to just have kind of a brief discussion around, but we're not going to dive into extra ICE tables for this. And then we're going to dive straight into the acid-base properties of iron salt and salt. So before we dive into new material, here is just a review of all the stuff that I really want you to bring in from last week. So what strong acids and bases are, that these dissociate completely, that weak acids and weak bases have partial dissociation. So that's where we need to pay attention to our Ka and Kb values. Conjugate base and conjugate acids are formed in an acid-base reaction. And then KEQ values, those are from a few weeks ago. And then remember that we were using Kas for acids and Kbs. Those are just specialized equilibrium constants. And then really big to remember, the stronger the acid, the weaker its conjugate base. And of course, you could flip these. The stronger the base, the weaker its conjugate acid is. That'll come back into play. All of this stuff will be reviewed as we go through the material. Okay, so for this first part, we're going to just do this as kind of a thought experiment. We're not going to go through and do the entire math here. So I'm going to kind of lead this discussion. The question is, how would you go about determining the pH of a solution that has 0.1 molar HCl? So that, remember that was on your list of strong acids, and then 0.1 molar of formic acid. And so we had learned last week that, well, we could determine the pH if we just had this amount of HCl, because 0.1 molar HCl means 0.1 molar H+, and then we can take the negative log of that to get our pH. Or if we had formic acid and we have the Ka value and our initial concentration, we can do an ICE table, solve for X, and then figure out X is equal to H+ concentration, take the negative log of that. Okay, so you all have done that a bunch, but now we've complicated the matter. So in past years, I've spent a bunch of time setting up an ICE table. And the ICE table, I'm going to go ahead and just do the base setup, but we're not going to solve the math. So if we think about this ice table, we'd say, well, we need to do an ice table for our formic acid. So we would set this up like this, and it reacts with water. And we have our H0 plus our CHO2 minus. So there's our conjugate base. And initially we were starting with 0.1 molar, and we're not going to count this. And we say we have 0 this. But if this is in a solution with 0.1 molar HCl, this value right here is no longer 0 because we have 0.1 molar HCl. And this kind of plays in to what we talked about with the Chatelain's principle last week in the lab. So if we have this in some sort of equilibrium and we add acid, it's going to push that equilibrium to the left. So now we've complicated matters with this 0.1 molar H plus. Everybody following that?
Kinda.
Thumbs up.
Is it 1 molar
Kinda.
because everything's a 1-to-1 ratio?
Yeah, so it's 1 molar because we have HCl going to H plus Cl minus. Remember, H plus is, we can use those two interchangeably. And we have that 1 to 1 molar ratio, just like you said, Desiree. Does that clarify it?
Yes.
Great. Okay, so now we have a much more complicated ice table. We have to like fill out all of this, and then we have to solve it. I trust that y'all can do that. So I'm not going to ask you to go through and do this whole problem. I'm going to tell you what the answer is. The pH, if you calculate this, okay, we're doing a solution of 0.1 molar HCl and 0.1 molar formic acid. The pH comes out to 0.992. Pretty acidic. Contrast that with the pH of just the HCl by itself, no formic acid. So that would be the negative log of 0.100. Oh, that's 1. So what this tells us as we go through all this math is that the formic acid really doesn't play a huge role in determining the pH when we have a strong acid. So the idea is when we have a mix of a weak acid and a strong acid, the strong acid is the one that just plays the bigger role, and we don't have to worry about using the ice tables and calculating in how much the pH would drop because of the additional weak acid. Okay. So pretty much what I was just telling you is a shortcut. When our weak acid concentration is about equal to the strong acid concentration, then just use the concentration of the strong acid. If the concentration of the weak acid is significantly higher than that of the strong acid, then we start needing to get into a situation where we do ice tables. And I'm not going to give you any problems like that. Okay? I'm bringing this up because maybe if you're in the MLS program, you might see some sort of problem later on about this, but you would get specific training in that particular problem, and there'd probably be an algorithm to calculate what you need to do. So I just wanted to let you know from a concept point of view, but we don't really have to do any of the math. Sound good? Okay, let's get into the significant details. Okay, so if we, oh, we're going to skip that too. Okay, so with polyprotic weak acids, this is where we get into that kind of interesting territory where we might have a strong acid and a weak acid mixed, or a weak acid and a weak acid mixed. And again, I'm not going to be giving you problems where you have to do ice tables with this, okay? So the only times where we're going to actually see these types of problems are when we have things like H2SO4, and then again, I'm not going to worry about that because it's just a math problem. Okay, so okay. Now I want to dive into the new material. This is stuff that is more likely things that you will see. So we're going to talk about the acid-base properties of ions and salts. So the whole idea here is that some ions can act as bases and some ions can act as acids. And so we need to be able to identify which ones can act as acids or bases, because we can change the pH of the solution without adding in what we commonly think of as an acid or a base. Okay, so here is a common example. We have a bicarbonate ion, okay, HCO3. If this HCO3 interacts with an H2O, this HCO3 minus will pick up a proton from H2O. It will form carbonic acid and OH minus. So we in fact have a basic solution. If we add a bicarbonate ion into a neutral water solution. Now, bicarbonate ions don't just exist by themselves. There's usually a cation associated with it, and most commonly we say NaHCO3. Okay? This is sodium bicarbonate. Anybody heard of this?
Yeah.
What is it commonly known as? Anybody know?
Is it baking soda?
This is baking soda. You got it. Okay, so sodium bicarbonate is just baking soda. Now this is an ionic compound, okay, so getting back to first quarter of Gen Chem. So it's going to completely dissociate, and we're going to end up with Na plus, oh hey, there's our bicarbonate ion. So this is how, when we put baking soda into water, we end up with a basic solution, okay? It's not because of the sodium bicarbonate itself is acting as a base, it's because the sodium bicarbonate dissociates into the bicarbonate ion and our spectator ion, Na+. So we often just leave that off. So now we've got our bicarbonate ion, which then can go into this reaction that we just saw, and we're going to make a basic solution. Okay, so again, our definition here of a basic solution is that we have a higher OH minus concentration than an H plus concentration. And this goes back to something that I said last week. If we add too much baking soda into our cookie recipe, our cookies are going to taste kind of bitter. And remember that basic things taste a little bit bitter. So we're going to end up adding too much of our base. So this is just a neat handwriting of exactly what we just did, showing our spectator ion. And here is our conjugate base of carbonic acid. And when we react our conjugate base of carbonic acid with water, we're going to form carbonic acid. Okay, so this example shows how an inorganic salt that is just an electrolyte, okay, remember electrolyte means it dissociates in solution, can change the pH of a solution by acting as a weak acid or a weak base. Okay, and we already answered this. Is the pH of the solution sodium bicarbonate neutral, acidic, or basic? This would be basic, which means the pH is going to be high or low.
Lower.
What do y'all think? Lower.
Less than
So we're
7.
going to have a low. So we're going to have above 7. Okay. pH is greater than 7 because lower than 7 or below 7 means that it's acidic. Above 7 means that it's basic. Okay. So let's kind of review what we just said. So with this example, we created an anion, okay? So we think of this as any anion can be thought of as a conjugate base of an acid. So again, we had our NaHCO3 to our Na plus our HCO3 minus. So here's our anion. So this is a potential conjugate base of an acid, okay? And we can think about this as all anions have a potential to act as a base. Not all of them will, okay? So we have to then think, well, what is the strength of that conjugate acid, okay? So remember, the stronger the acid, the weaker the conjugate base. So if we have an acid like HCl, it's going to go to H plus Cl minus, okay? Remember, the Cl minus is the conjugate base of a strong acid. So if we did something like added NaCl, if we wrote sodium chloride and we put salts into water, we'll have Na plus ions and we'll have Cl minus ions, okay? Now this is, Cl minus is also an anion, just like our conjugate base of carbonic acid was, or our bicarbonate ion. But this will not act, the Cl minus will not act as a base. Because it's the conjugate base of a strong acid, and remember, we have complete ionization. The stronger the acid, the weaker the conjugate base. So a conjugate base of a strong acid is so weak that it will not act as a base in solution. So what we're looking for, if we're trying to decide if an anion is going to act as a base, remember all anions have that potential, we're going to look at the strength of the conjugate acid. If it is a weak conjugate acid, then our anion does act as a base. If it is a strong conjugate acid, then no, our anion does not act as a base. So this slide is pretty much what we just wrote out. The stronger the conjugate acid, the weaker the base. Therefore, anions that are conjugate bases of weak acid can act as bases. Does that make sense to y'all?
Yep. Just have to work on remembering each part.
Exactly. One of the nice things about COVID times, you don't have to memorize this because there's not going to be any closed book assessments. It's just a matter of like wrapping your head around it. Yeah. Okay, so we just did this for anions. Okay, so we're talking about anions here, and that anions have the potential to act as bases. So now we need to think about cations. Oh, before I do, here's a great figure. So this is a fantastic figure for you to all use on quizzes and assessments. So here are our acids, and here are the conjugate bases of those acids. So what we looked at here was HCl minus. So we're saying, okay, well, here is a strong acid, and here's the anion. Okay, so we can think of all these potential bases as anions. Okay, so here Cl minus doesn't act as a base. We say that's neutral because the acid is strong. So here are some other examples of acids where they end up acting neutral conjugate bases. And then bicarbonate, let's see. Here we go. So HCO3. So here is our carbonic acid, and here's our bicarbonate ion. And this is a weak acid, so it's under the weak acid designation. So therefore, this anion will act as a base. It acts as a weak base. Okay? So this will hopefully help you in your assessments. Okay. Okay, let's do this problem before we talk about cations as weak acids. So this problem should be very similar to what you worked on last week. However, it adds a little bit of a flip here because I'm giving you the Ka of formic acid. Here is our conjugate acid, but I'm asking you to figure out the pH of the solution with sodium formate. So I want you all to take like 2-3 minutes, try and figure out a plan. You don't have to start doing the math. We'll do that all together, but please try and figure out how you're going to tackle this problem. I'm going to mute myself. Y'all are welcome to talk amongst yourselves, and then I'm going to come back and interrupt you in like 3 minutes. All right, anybody come up with something they want to share?
I think I'd start out by finding the pH of this sodium for me. The actual number, because it's 0.1 molar. I'd start by finding the pH of that.
Okay.
And then,
so,
yeah, that's how.
Okay. Well, so this, defining the pH of this, is this a strong acid or weak acid or strong base or weak base? So you're right. That is what we want to do, but I think there's some steps in there. So let's think about what this is. This is an electrolyte. But we can't right now say that, hey, this is, it's in and of itself, it's not an acid or a base. So let's write out the reaction that's going to happen. And Desiree is right. We want to find the pH of this. But it's not quite as simple as saying 0.1 molar is, we can't take the negative log of 0.1 molar because we are not having a one-to-one stoichiometry. Okay. So if we have our NaCHO aqueous, this is going to dissociate into Na plus aqueous plus CHO2 minus aqueous. Okay. Now we can identify that, hey, here is our anion. It has the potential to act as a base. Okay. So now what are we going to do? Anybody get this?
Professor, I'm sorry, we can't hear you very well.
Oh, really? Oh,
Or it could just be me.
are you all? Yeah, hold on. Is my sound quality bad for everyone?
Yeah, it's like a static in it.
Yeah, interesting. My husband told me he gave me the nice headset this morning. Okay, give me a second. Okay, everyone, give me a second. I'm gonna hang up on my phone and try and just get on the computer audio.
Okay, can you all hear me? Is it any better?
Yeah.
Much better.
Okay, sorry about that. Anytime that happens, please let me know right away. This headset must have gotten into the baby's mouth. My child really loves to suck on our headsets. And my husband told me he gave me the nice one that she hadn't had access to, but maybe she had access to that one. Okay. So with this particular problem, we've now identified that we have an anion that has the potential to act as a base. So did anybody dive into this problem any farther? What else did you do after this?
I'm trying to figure out how to work with the Ka. It seems like it's much smaller than the 0.1 molar.
Absolutely, it is much smaller. So this is a lot smaller than the 0.1 molar, which does mean that when we get to the ice table and the calculations, we can start making some assumptions. Good identifying that. So before we set up our ice table, I think the next thing to do is to say, hey, well, the Ka is actually for formic acid here. Yeah. And what we're really interested in is how basic this solution can be. So what we've identified is that we have an anion here that can potentially act as a base. And so we're actually going to end up wanting a Kb value because the reaction that we're saying may happen here is that this will react with water and it will abstract a proton and will make formic acid plus OH minus. Y'all kind of following that thought process? That this anion can act as a base. So this is this anion here. It reacts with water and picks up a proton, and now we've formed formic acid. Okay, and we have our OH minus. You kind of see that?
Yeah.
Cool. So if we started out with 0.1 molar here, that means we have 0.1 molar Na plus. We're going to ignore that for now. And we have 0.1 molar of our formate ion. So that means if we are doing an ice table, we can say, okay, well, we have 0.1 molar of our formate, which has the potential here to act as a base. We're not going to count the concentration of water. And our initial concentration of formic acid is 0, because remember, we have a solution of sodium formate. And I'm giving you the Ka of formic acid, but we didn't start with any formic acid in our solution, okay? So that means both of these concentrations here are 0. So now we set up a pretty standard ice table like we did before. We're going to say, well, depending on what this equilibrium value is, we're going to lose some of our formate. Okay, we're not going to count water. We're going to gain some formic acid. We're going to gain some OH minus. And at equilibrium, we'll have 1.10 molar minus X for our formate ion. We'll have X for our formic acid, and we'll have X for our OH minus. But we were given a Ka for this. We need a Kb now. So our Ka is 1.8 times 10 to the minus 4. But remember at the very end of class last week, we said, oh, Ka times Kb for our conjugate acid base pair equals Kw. So we can calculate our Kb by saying that's just Kw over Ka. Y'all following that?
Yeah.
Great. So we're going to just do that math really quickly. Our Kb is 1.0 times 10 to the minus 14 all over 1.8 times 10 to the minus 4. And we'll end up with a 5.6 times 10 to the minus 11. Wow, really small. Okay, so now this is telling us this is way smaller than our 0.1 molar. So we're going to go ahead and make that assumption. So let's say so when we're solving for X, we can assume that X is much, 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 much smaller than our 0.100. Okay, so that allows us to set up our KB equation now, 5.6 times 10 to the minus 11, to just say that's X squared over 0.1. Because we initially had that 0.1 minus X, but we make that assumption. So that simplifies that entire equation. So now to solve for X, we can say X is equal to the square root of 0.1 times 5.6 times 10 to the minus 11. So this math, X is equal to 2.4 times 10 to the minus 6. Okay, what do we do now? Where did this get us? Like what does X mean? Let's come back to the concept because it's really easy to get lost in the math here.
I have a question.
Yeah, go.
Where did you get KW from?
Oh, so KW, kind of coming back to last week, KW is that, oh man, KW is the auto ionization constant of water.
Oh, okay.
And that is standard of 1.0 times 10 to the minus 14. And that's just a value that can be figured out in the lab and just one to remember.
Okay.
So that,
And then when you were solving for X,
yep.
why was it X to the 2? Like on the first one?
Yeah, great question. Okay, so remember that our KEQ is the concentration of the products taken to their stoichiometric coefficients over the reactants taken to their stoichiometric coefficients. Okay, and in this case, our products, we have HCHO2 and we have OH minus. Each of those were X. So when we calculate our KB, that's going to be X times X all over, because this is our concentration at equilibrium, all over our 0.1 minus X. X times X is X squared. And then we make that assumption that X is much smaller than 0.1, so we can just say 0.1 there.
Okay, I got it.
Yeah, does that answer all your questions?
Yeah.
Okay, great. We're gonna just keep this and we're gonna just write clarification. Okay, that way it doesn't, if you go back and look at the notes, it doesn't screw you up, okay? All right, so back to X. What is X? What is it representing here? We solved for it, so it must be important.
Is it concentration?
Yeah. Concentration of what? You got it. It's concentration of something we really want. It's the concentration of our HCHO2, but it's also the concentration of our OH minus. So let's come back to this question. The question says find the pH. Okay, so we want to figure out the pH of the solution. I'm going to say we're making a buffer or something with sodium formate, and we want to know if it's the right pH for what we're making. And we have calculated now our OH minus concentration. Well, remember that pH is defined as the negative log of H plus, okay? And remember that pH plus POH equals 14. And the POH is simply the negative log of the OH minus concentration, which is what we have right here. So if we say, okay, well, we have our OH minus concentration, that's 2.4 times 10 to the minus 6. We can calculate our POH to then be the negative log of our 2.4 times 10 to the minus 6. So our POH should be just under 6, 5.627. I'm sorry, that's our POH. And now we can calculate our pH by saying that's 14. 14 minus our 5.627. We can calculate our pH to be 8.37. Our last step here is to do a concept check. Is this acidic or basic?
Basic.
It's basic. You got it. So now let's go back up to the question. Would we anticipate we have an acidic or a basic solution based upon what we have put into our aqueous solution? We've put a strong electrolyte in. That strong electrolyte dissociated into Na plus and a conjugate base of formic acid. So we've put an ion in that can act as a base because it's the conjugate base of a weak acid. So we would expect a basic solution. So our concept check makes sense. You follow on that?
Yep. Can you scroll down so I can see the calculations of pH? Thank you.
There you go. Okay, so this problem is pretty much the same as what we did with our ice tables last week. The only thing we added to it was that first step of saying, hey, this is a strong electrolyte. It's going to dissociate into a cation and an anion. Then we identified that that anion is the conjugate base of a weak acid.
Okay, I'm done with the notes. Thank you.
Okay, everybody in a good spot to move on?
Yep.
Greg, Irisha, Kayla?
Yep.
Great. Thanks, y'all. Okay, so we now just identified how anions can act as weak bases, and the same thing is true with cations, okay? So every cation can be thought of as the conjugate acid of a base, okay? There we go. Now, again, we're saying that pens are just being really strange. Let's move them away. Okay, so now we're saying that all cations have that potential to act as an acid. So this is the exact opposite of what we were looking at before. So let's just take an example. If we have NH4+, this is the conjugate acid of NH3. Okay, so if we're adding, say, NH4Cl into solution, it can then dissociate into NH4+ plus Cl minus. Okay, and we have water. So the water can act as a base, picking up the proton off of the NH4. So we'll end up with H3O plus plus NH3. We still have our Cl minus, that's our spectator ion. Why is Cl minus a spectator ion? Now this is an anion, and we just learned that anions can have that potential to act as bases. Why is Cl minus not acting as a base here? What's the conjugate acid of Cl minus?
HCl.
You got it. It's HCl. Strong acid, weak acid.
Strong.
Strong acid. Okay. That means it's going to completely dissociate. So that means Cl minus is too weak to act as a base. So all we have here is the cation that can potentially act as an acid. And we see that it does because the cation is a conjugate acid of a weak base. So what we'd end up here is with an acidic solution. Y'all following that same logic?
Mhm.
Cool. Okay. So again, this depends on the strengths of the conjugate base. The stronger the conjugate base, the weaker the acid. Therefore, cations that are conjugate acids of weak bases can act as acids. So this is the exact same thing that we just saw, but we're just looking at cations instead of anions. Okay. So I could potentially give you a problem just like I gave you the one with the conjugate base of formic acid. I could give you a similar problem where we're looking at the cations instead. Okay, so I just want to kind of go over what we just talked about. These are kind of a set of rules. This may be something that you want to keep up when you're doing assessments. So if the salt, if the cation in that salt is the counterion of a strong base and the anion is the conjugate base of a strong acid, it's going to form a neutral solution. Okay, so we saw that with like NaCl. We put NaCl in water, it is neutral. Okay, so we have here strong acids and bases. We'll end up having a neutral solution. If the salt cation is a counterion of a strong base, okay, so that means that that cation is so weak that it can't act as an acid, then we now have an anion that is the conjugate base of a weak acid. That means that anion can act as a base and will form a basic solution. So some examples here: NaF, calcium acetate, KNO2. If the salt cation is the conjugate acid of a weak base, okay, so weak base means that the conjugate acid is also weak, it can act as an acid, but the anion is the conjugate base of a strong acid, so nothing is going to happen here, will form an acidic solution. And this is the example that we just saw. Okay, so these are those set of rules for identifying if we have salt solutions, if they're acidic or basic. Questions there?
And what slide is this?
26.
Thank you.
Yeah, slide 26. Okay, so part of why I teach this, because I think this is really important to our everyday lives. Many of the natural pollutants that we see that come from natural processes and not unnatural processes are actually, when they're dissolved in the air, these are non-metal oxides, and these are actually acidic. So for example, if we have CO2, we've heard a lot about CO2 in the atmosphere. If we have CO2 gas and it reacts with water, we're going to end up with carbonic acid. Okay, we've already seen carbonic acid is acidic. It's a weak acid. Okay, SO2 is another common pollutant. And if we have 2 moles of SO2 and it reacts with O2 gas plus water. Sorry, that's messy. That ends up going to sulfuric acid. And this is a polyprotic acid. And then we have NO2. This is something that comes out of our tailpipes when we drive, reacts with O2 gas, and then it rains, so we have water. We've now made 4 moles of nitric acid. All of these things are bad news, and will make the rain acidic. So as it rains, these dissolved gases, they're dissolved in the air, it starts to rain, we have these reactions occur. All of a sudden we have something called acid rain. And this is in general not very good, and it can be naturally occurring. So things like volcanoes and some bacteria actually do make these natural pollutants. The main problem is when we make a really high concentration of them from processes that aren't naturally occurring, such as the combustion of fuels from coming out of the tailpipes of our cars. So here's just a figure showing that. This is kind of a cool figure showing that we have our SO2 and our NOx. So NOx can be NO or our NO2s, plus remember we have CO2s that contribute. Here again, we are showing natural sources and non-natural sources. Pollutants come up in the atmosphere, so we're reacting with O2, and then as soon as it starts to rain, now we have a reaction with H2O and we're getting acid rain. This is just a really interesting figure from a textbook that I found. It's a little bit of an old figure, but it's showing the H+ concentration in the rain for different regions in the US, and we're kind of in the sweet spot here and in the Pacific Northwest. But if we look up here in the Northeast, there's a lot of industry a little bit farther down, and in the Midwest as well. And those, because of the atmospheric movement of air, it moves this direction. So those pollutants are actually brought up into the Northeast, where then it rains and they end up with a lot of acid rain. Thankfully, some policies work. So the EPA regulations that went into effect a number of years ago have actually functioned to reduce the concentration of these pollutants in the air. I have this note that this ends in 2013, and so an updated graph. I'm not sure what these results are. I need to go see if I can find an updated figure of this, and if it spiked as EPA regulations were decreased over the last decade. Okay. Questions, thoughts, comments? Yes, I think it's break time. Let's take, it's 10:30, so let's come back at 10:40. Does that sound good? A little more than a 10-minute break? Go stretch your legs, grab some coffee, whatever you need, and then we're gonna talk about buffers. All right, welcome back, everyone. Do we have everybody here? Thumbs up if you're here. Or say something. Greg, Chelsea. You both still getting coffee? Okay, while we're waiting for Greg and Chelsea, did anybody do anything fun this weekend? No?
Planted more veggies.
All
That's
right.
kind of it. Yeah.
What do you have in the ground so far?
Beets, cauliflower, all the cool season stuff.
Yeah. All the breath.
Yeah. Mm-hmm.
Yeah. Oh. Yeah, I got a lot of I got most of my cauliflower starts put in the ground this weekend too. That's so exciting. It's like one of my favorites.
Yeah. Yeah.
I have yet to be very successful with broccoli though. Man, I don't know what it is. Broccoli's so hard to grow.
Huh. Yeah, I hear it is. Last year was really successful, so we're gonna go do a lot this year too.
Awesome. Well, I may ping you if I can't get it this year.
Yeah.
See.
Did you do it in the summertime or this? I'm pretty sure you started in the spring, right?
Yeah, yeah. Spring is when
Yeah.
we usually start it.
Yeah.
Yeah.
And we actually did ours like kind of in the middle of summer because we got it late.
Oh,
And it still worked out really well. So I'm surprised.
Interesting. Well, maybe that was
Yeah.
the key. Well, we'll see how mine do. I'll message you if
Yeah.
like tell me what you did.
Yeah.
All right, Chelsea, Greg, are y'all back?
I'm back.
All right. Greg, are you here? No, Greg? Okay, well, we're recording, so hopefully y'all can just, if he's gone, he can go back and watch this again. All right, hopefully everybody's caffeinated up if you need to be and ready to talk buffers. Okay, so buffers are super important in the chemistry lab, especially the biochemistry lab. So those of you that are moving forward into biochem, this is really an important topic to pay attention to, and it's going to come up again. For those of you that aren't moving forward, buffers are still really important because we wouldn't be alive without them. So buffers, our blood is a buffer, one of the most important buffers in our body. Buffers are things that maintain a target pH range, okay? So they're solutions that resist some sort of pH change, and they're super important to life as we know it, okay? So to make a buffer, we combine a weak acid and its conjugate base. So we can do that in the lab. If we look in biochemistry and in biology, that's exactly what we see when we have a buffered solution. And so let's look at an example here. If we have acetic acid, which is a weak acid, so HC2, H3O2. So this is acetic acid. And it is in some sort of equilibrium with its acetate ion, so C2H3O2, okay? And if we're doing this in the lab, we're probably using sodium acetate, so Na+, C2H3O2 minus, okay? So acetate ion is our conjugate base. And as we just learned, our Na+, it's a cation, but it's the conjugate acid, the conjugate base of a weak, conjugate acid of a weak base of a strong, let me start that over. Na+ is a cation. It is the conjugate acid of a strong base. Therefore, it is not going to act as an acid. Okay, so we can just say this is our spectator ion. now that I have my language back. So if we have this in some sort of equilibrium, we have our acetic acid in equilibrium with our sodium acetate or our acetate ion, and say we were going to add some HCl, a small amount of strong acid, our HCl is going to react with our sodium acetate, so we'll end up making some more acetic acid. And then because we have our spectator ion here, that would complex with our Cl minus, so we'd end up with NaCl, okay, also aqueous. Conversely, if we add a small amount of a strong base, NaOH, that's going to then just react with the acetic acid, and we'll make H2O plus NaC2H3O2, which is our sodium acetate. Okay. So what happens here is that we end up with a small change in our equilibrium. Okay, so we started with a weak acid and conjugate base in equilibrium. And just like y'all did in lab, we disturbed that equilibrium by adding either a small amount of acid or a small amount of base. But what happened is we've got our weak acid, weak base in equilibrium, and they reacted with our acid, our strong acid, or our strong base. So we have a small shift in equilibrium when that happens. Which means we'll have a small shift in pH. But conversely, if we were to put that same amount of either HCl or NaOH just in water, we would have had a much larger shift in pH. Okay, so the shift that happens when we have a buffered solution is much smaller than the shift that we would have if we had pure water. Okay, so the buffer resisted that pH change. Okay, so we're going to look at this a little bit more in detail. And this is an example of Le Chatelier's principle occurring. And we call this another name, sorry, there's so many definitions and names, we call this the common ion effect. So we have some suppression of ionization of a molecule due to a common ion that is part of an equilibrium, okay? So if we just had, so kind of coming back to this same reaction here, if we just had in this reaction just this acid, okay, then our reaction would only progress to the right. But because in this previous example, we had both the acid and the base, and we have this conjugate base, And this is our common ion. So when we already have this ion, the equation will find an equilibrium based upon the concentration of all the constituents, okay, based upon the Ka. Okay. And so therefore it will resist that change as if we would have added acid. In this case, it's going to resist that change because we have that common ion, where that is not the case if we only have one of the species. So let's look at this a little bit more in detail. If we have a reaction, so let's go ahead and start with that exact same reaction that we had here. We react our acetate so we have our acetic acid and our acetate ion, and say we've started out with a buffered solution, so we have 0.100 molar of each of these constituents. Okay, we're not going to count water, and say we have about 0 of our H3O plus. Okay, so we've started out with our buffer situation where we have our weak acid, weak base, but we haven't added any of our acid. So we can calculate the pH of this buffering solution by saying, okay, well, we have minus X. We have no change there. We have plus X. We have plus X. We have 0.001 minus X, X, and 0.100 plus X. Okay? And we can say, well, our Ka is equal to 1.8 times 10 to the minus 5. Okay? We can assume that X is much, much smaller than 0.100. So we can set this up to say, okay, we have X times 0.100 over 0.100. We solve X ends up being our Ka, 1.8 times 10 to the minus 5, is because those two cancel. We can calculate our pH then to be the negative log of 1.8 times 10 to the minus 5. And our pH is now 4.74. Okay, don't worry, we're not going to have to do this for every single buffer. I'm going to show you a shortcut, okay? So what this is telling us is we can make a buffer with a pH of 4.74 if we have 1-to-1 stoichiometry of our acetic acid and our sodium acetate. Okay, but we may want buffers that have different pHs, and so we can do a bunch of different things. We can change the concentration of our acid and our conjugate base, or we can choose a different system that has different Ka value and therefore would have a different pH. So before we dive into all of those things, I want to show you the shortcut so we don't have to do this whole ice table every time we make a buffering solution. So if we assume that X is less than 0.1, which is a good assumption to make for most weak acid, weak base pairs, we can use this equation called the Henderson-Hasselbalch equation. I'm not going to derive it for you. It's actually not too hard of a derivation and it should be in your textbook. So if you want to go look at it, you're welcome to. or you can ask me and we can go over it in office hours. But it does require the assumption that X is a lot smaller than initial concentration. Okay, so that does usually work unless you pick a huge concentration difference between your conjugate acid and conjugate base. Okay, so here's what Henderson-Hasselbalch is telling us. It says that the pH, the final pH of our solution, is equal to the pKa, remember that's the negative log of the Ka, plus the log of the concentration of the conjugate base over the concentration of the conjugate acid. Okay. So this is a really great way for us to say, okay, well, we can, if we know the Ka or the pKa, and we know the concentrations, we can figure out the pH of that solution. We could also do this backwards and say, well, we want a certain pH and we have the pKa of the acid, we know that. We can figure out the concentration of the base and acid that we need to put into our solution in order to make the buffer that we want. So let's go ahead and work this problem together. We can use Henderson-Hasselbalch to calculate the pH of this buffer solution if we have 0.05 molar benzoic acid and 0.150 molar sodium benzoate. Okay, which one of these is the acid and which one is the base? Anybody want to take a guess? We have sodium benzoate and we have benzoic acid.
Isn't the first one the acid?
Yeah. It wasn't a trick question, I promise, okay? So this is the hardest part of this, is identifying which one's the acid and base. And as Irisha pointed out, usually it's gonna have the name acid in it, okay? So we have a Ka value. Remember in Henderson-Hasselbalch, we use a pKa, so we need to make sure that we take the negative log. So the pKa of our acid is the negative log of 6.5 times 10 to the minus 5. Okay, so we're going to plug that into our Henderson-Hasselbalch. So pH is equal to our negative log of 6.5 times 10 to the minus 5 plus the log of the base goes on top. Okay, so that's going to be 0.150 molar over the acid, 0.050 molar. And if we plug and chug this, we should get a pH of 4.6, sorry, too many fours, 4.66. Okay. So I did say memorize this, but again, you're not going to have any closed book quizzes. So this is another one of those, slide number 36, maybe one that you put on your Post-it note or have right next to your computer so you can use this equation. Okay, so now let's talk about how this works. So remember, we have a buffer that's going to resist a pH change, but the pH still does change a small amount. So let's look at this from a pictorial representation and then we can look at it mathematically. So if we start out with equal concentrations of the weak acid and its conjugate base, just as we showed earlier, okay, from a molecular scale, here is our molecules of acid, here's our molecules of base. Okay, so now if we add OH minus, we're going to end up deprotonating some of the acids and making a few more of our conjugate bases. So we'll have now, instead of 4 and 4, we'll have 3 and 5. So if we were doing this, we would have a different, slightly different concentration. Now the Ka is still the same, but we could use Henderson-Hasselbalch to calculate our new pH based upon these two concentrations that have changed. Similarly, if we add H+, now we have protonated some of the conjugate bases, so we have more molecules of acid than we have molecules of base. And again, we can use Henderson-Hasselbalch equation with our pKa that we started out with, just representing now we have a few more moles of HA compared to A-. Okay, so we're going to calculate the change in pH of a buffer. This is, you're going to probably do a number of these in discussion section as well. Okay, and there's 3 steps. So the first step is to calculate that initial pH of the buffer solution. Then we have to do a stoichiometry calculation. This is different than an ice table, okay, but it's going to look somewhat similar to an ice table. So the setup looks similar, but instead of an equilibrium, we're shifting our equilibrium, okay? And then we're going to perform an equilibrium calculation using those new values, okay? So we're going to walk through an example. So if we have 0.01 moles of NaOH, so this is our strong base, and we add it to an already made buffer solution. Oh, hey, we've seen this before, yeah. This is our acetate and our sodium acetate, okay? So we have them an equal concentration of 0.1 molar, okay, in a 1 liter solution, okay? So the whole idea is the pH of that whole solution after the NaOH has been added. Remember, we have to do this in 3 different steps. So that first step is to calculate that initial pH of the buffer solution. So we're going to say, okay, well, we have our acetic acid, in some sort of equilibrium with our sodium acetate, and we're starting out with 0.100 moles, but it's molar because it's in 1 liter. So 0.1 molar, 0.1 molar, okay. So our Henderson-Hasselbalch, for this first step, we're going to say our pH is equal to our pKa plus the log of our base over our acid, okay. Well, base over acid, this is 0.1 over 0.1, okay? So rule of logs, log of 1 is equal to 0. So that means if we have equal concentrations, our pH equals our pKa. And we saw that earlier in that proof of principle that we started out with, okay? So therefore the pH of this initial solution just equals the pKa, which means that we'll calculate it by taking the negative log of our Ka, which is 1.8 times 10 to the minus 5. I didn't give that to you here. We've been working with this solution for a little while. So this is the same one that I gave to you earlier. So the pH of our solution is 4.74. Okay, and that's what we calculated earlier. Great. So now we're adding 0.010 moles of our NaOH to our buffer solution. So this is the challenging part. We're going to do not an ice table, we're doing a stoichiometry table. So the thing to remember when you're doing a stoichiometry table You must use moles, not molar. Okay, so we're using number of things, not concentration. Okay, so the stoichiometry table allows us to determine the moles, the number of moles of our weak acid that have been converted to our weak base. And we know that's what's going to happen because we're adding a strong base. So our strong base will react with our weak acid to form our weak base. Remember, the whole idea here is we want to be able to, in our last step, use Henderson-Hasselbalch again to calculate that pH based upon our new concentrations of our weak acid and our weak base. So here's the reaction that's happening. We have OH minus. I'm getting rid of the Na plus because it's a spectator ion. Okay, so this is from our added NaOH. It's going to react with our acetic acid. Okay. And here is our base, here's our acid. Remember, back to our definitions, our acid's a proton donor, our base is a proton acceptor. So we're going to end up with water and our acetate ion. Y'all, why did I just do a single arrow here? Why did I not do equilibrium arrows? Anybody have a guess?
Because the rate of the backwards reaction might not be the same.
It's not going to happen at all. So
Oh.
yeah, exactly. So this is a strong base and we're not going to go backwards. We're not going to form that strong base. So we're not in equilibrium. This equation is going all the way to the right. Nice. Okay. So before we added the OH minus, we had no OH minus in there, yeah? We had 0.100 moles. Remember, we're doing this in moles, not molar. We're not going to calculate the water. And we also had 0.100 moles of our conjugate base. Yeah? Okay, so this is just kind of truism. This is setting up that problem. Remember, we started with 0.1 and 0.1, and this is before we've added it, so we say that as 0. Now, what we're going to add is the OH minus. We're going to add 0.010 moles of our OH minus. We're not adding anything else. So then we have our after. Well, after, again, as we just pointed out, we're not going to go backwards. All of this OH minus is going to react. So it's gone. 0 moles of that. All of our strong base reacts with our weak acid. Okay, so in order to calculate our after, we're going to say, well, we started out with 0.1 moles of this, and we're going to react 0.010 moles of OH minus with 0.101 moles of our acetic acid, because this is 1-to-1 stoichiometry. So we would expect to have 0.090 moles of our acetic acid left over. We're not counting water. Now, every mole of this that we've reacted with this, we're making 1-to-1-to-1 stoichiometry of our acetate ion. So we should have 0.1 0.110 moles of this. Is everybody clear where I got these values? This is the important part.
Nope.
Okay.
I don't know. Yeah, that 0.090.
Yeah, let's do it again. And let me do it again in a little bit different of a way. Thank you for telling me that that wasn't clear. Okay, so if we have our OH minus react with our acetic acid, this is a 1-to-1 molar ratio. That means we're going to have none of this left because we started out with more of this than we had this. And so we're going to end up with, for our acetic acid, we're going to have 1.000, that's what we started out with, minus 0.010 moles. Ah, don't delete it. There we go. This is happening because all of our strong base is going to react with our weak acid. So we're not going to have any strong base left over. We end up with 0.100 minus 0.010 is 0.090 moles. You see where I got that 0.090 moles now?
Yeah, makes sense. Thank you.
Perfect. Okay, so then for our acetate ion, we started out with our 0.100 moles, but we're going to add to it 0.010 moles. So our final number of moles is going to be 0.110 for our acetate. Now, is everybody clear how I got that value?
Yes.
Thank you. Chelsea, Irisha?
Yes, for sure.
Yes.
Fantastic. Okay. So now we have new populations of our weak acid, weak base. Now we get to calculate our new pH. So we're going to perform equilibrium calculations of our H3O plus using our new values, okay? We have two options. We can use an ice table, which hopefully y'all are like super experts at now, or we can take the easy way out and use Henderson-Hasselbalch. That's my go-to. Okay, if I know I'm going to do the assumption, then I'm going to just use Henderson-Hasselbalch. So now our pH is equal to the pKa plus the log of the base concentration over the acid concentration. Now these are different. They're no longer equal. Okay, so we're going to say our pH is equal to our pKa, which is 4.74, plus the log of 0.110. Wait, isn't this moles? This needs to be concentration. Oh, right, this whole thing was in 1 liter. So this is actually in molar, okay? Be careful when you do this transition. It's easy to take a step and be like, wait, maybe I'm not doing it in 1 liter, okay? So 0.110 over 0.090. Okay, let's predict this. All of a sudden, so our pH was 4.74. We now have added some base in. And so if we add base in, we're going to expect that whole solution to become more basic. Does that make sense? You add base, solution becomes more basic.
Yeah.
Perfect. So before our pH was 4.74, so we're guessing that it's going to be a little bit higher than 4.74, but because we're doing this in a buffer, it's probably not going to be a huge pH change. So something slightly bigger than 4.74. Okay, so now if we crunch these numbers, we should have pH is equal to 4.74 plus log of 0.11 over 0.09 is 0.087. So our new pH should be 4.83. So we had a change in pH of 0.087 pH units. What does that mean? We have no context to put that into. We just did some math. That's awesome. We did some math. Let's put this into context, because the big question is, what would the pH change be if we added that 0.1 moles of NaOH to 1 liter of pure water? Okay, so this is the whole idea of a buffer. I told you buffers are important. Let's see how important they are. We had a change in pH of 0.087 pH units. If we started with pure water, pH of 7, okay, and we added 0.010 moles of OH minus in 1 liter of solution. Okay, that's 0.010 molar. Well, then we can calculate the pOH by saying that's the negative log of 0.010 molar. Okay, that's 2. The pH is simply 4 minus the pOH, so or 14 minus the pOH. Oh my. So change in pH was 12 minus 7, 5 pH units. Same amount of NaOH added to pure water, we get a change in 5 pH units. Pretty significant change. If we add it to our pretty weak buffered solution, all of a sudden we have a 0.087 pH change. That buffer really worked to resist that pH change. That's kind of awesome, yeah? If we were all in the classroom together, I could probably see how stunned and amazed you would be about how functional pH or how functional buffer systems are. They're amazing. I'm just going to pretend you all have like really big grins on your faces and are just so excited. Okay. 11:20. Yeah, let's keep going for a little bit longer. So, buffer capacity. So you can imagine in this last example that if we put way more NaOH in, so more than 0.010 moles, it would start to change the pH a little bit more. In fact, we only have a certain amount of capacity within this buffering system because we only have 0.1 moles of our acid. So the key here is that our perturbation of our strong base or our strong acid that we're adding in to our buffering system is much smaller than our initial concentrations of our buffering system. So this is something that we call buffering capacity. So this is the amount of acid or base that we can add to a buffer without causing a large pH change. By large, this is a relative term, okay? So this depends on what your system is. Will your system, i.e. your body or your experiment, break and no longer work with a pH change of 1? Then we're going to consider that to be a large pH change. We need a bigger buffering capacity to prevent that pH change of 1. Or maybe in your experiment, you can have a pH change of 5 pH units or only a pH change of 0.05 pH units. Okay, so we start thinking about what buffering capacity we need in order to maintain a certain pH range. So there are two ways that we can increase the capacity of a buffering solution. Anybody want to take a guess of what those are? No, I gave you a big hint just now.
Add more buffer.
Add more buffer, increase concentration. That's the big one, okay? 1, increase concentration of buffer constituents. Okay, because again, that relative number of moles of conjugate base and conjugate acid needs to be smaller when our strong, needs to be relatively larger than when our strong acid or strong base is added. Okay, so we need strong base or strong acid to be much lower than our buffering components. Okay, the other thing, I wasn't expecting y'all to get this one. Remember, we had our Henderson-Hasselbalch where our pH is equal to the pKa plus the log of our base concentration over our acid. And we said, okay, well, for log where our base and our acid are the same, then that means the ratio of base and acid is 1, and log of 1 is equal to 0. So then the pH is equal to the pKa. That is our ideal situation. It's not going to be practical to do that every single time. Okay, but if we have equal concentrations of acid and base, that means we have equal buffering capacity for adding a strong acid or adding a strong base. Okay, because buffering capacity can go either direction. So the closer base over acid is to 1, the closer that ratio is to 1, the more efficient the buffer. Okay. So rule of thumb is no more than a 10-fold difference between the two concentrations. Okay. So we can start to think about what our target pH is, then pick a buffering system where the pKa of that conjugate acid is similar to the pH. Then we'd calculate the base acid ratio, and then we'd crank that concentration up as high as our system can allow it. Now there's going to be different things we have to think about. We don't want too high of concentrations because then we can have some osmotic problems with cells, or maybe it's really expensive. Okay, but we start to like titrate in all these different parts of a buffer system. Okay, so again, just as a review, the first one that Greg came up with was increase that concentration of the buffering agents, right? We have a more concentrated buffer, it's going to have a higher buffering capacity. And then the second one is when we're choosing an acid to make a buffer, choose the one whose pKa is closest to the pH of the buffer, and then use, again, those high concentrations of those buffering agents. So quick practice problem. I think I'm gonna have you all do this one. Let's take just like 3 minutes, read this problem, and then come up with what you think the best answer is. Okay, I just put up a poll, vote for your favorite acid. And remember, this is an acid base, conjugate base buffering system based upon this question. So chlorus, nitrous, formic, or hypochlorous. Which one of these systems would you choose to make a solution buffered at pH 4.25? Only one of these. Oh, here we go. We've got 2 responses, 3 responses. Okay, one more person needs to vote. All right, we have everybody. Okay. And Pauline, share results. There we go. Can you all see the results?
Yeah.
Yes.
Awesome. Okay, so one of you said chlorus, one of you said hypochlorous, and 3 of you said formic. So let's see. In this case, we want a solution of a pH of 4.25. And the idea is, 1, we're going to bump up that concentration as much as we can. And 2, we want a buffering system where the pKa of the acid is as close to this pH as possible. So right off the bat, I can say it's not going to be chlorus and it's not going to be hypochlorous because those are both pretty far away. And then the next step is to look at the difference between nitrous acid and pKa and our desired pH, and our formic acid pKa of 3.74 and 4.25. And if we do this math, we can see that formic acid is slightly closer in pKa. So this is going to be our answer of formic acid. That all make sense to y'all?
Yep.
Awesome.
Yeah.
Cool. All right. Let's see. I think I want to send you all out for a quick break. Let's do another 10-minute break. So 11:40, and I'm going to spend that time looking through what all we have to cover for the rest of this unit, so I can decide where we are going to stop for the day. So I'll see y'all back at 11:40.